Hello everyone, welcome to National Standard Examination in Physics 2011. A piece of N-type semiconductor is subjected to an electric field Ex. The left end of the semiconductor is exposed to a radiation so that the electron-hole pairs are generated continuously. Let N be the number density of electrons. The electron current density Je is given by Je equal to En mu E Ex plus E dE dN by dx. The dimensions of electron drift mobility mu E and electron diffusion coefficient dE respectively are. Applying principle of dimensional homogeneity, En mu E Ex is current density. So current density is I L power minus 2, that is equal to En mu E Ex. Upon writing the dimensional formula for other quantities, we have mu E as m power minus 1 t square I power 1. Applying the principle of dimensional homogeneity for the second term, we get I L power minus 2, that is current density, equal to E into dE into dN by dx. By writing the dimensional formulas again, we get dE equal to L square t power minus 1. A metal sample carrying a current along x-axis with density Jx is subjected to a magnetic field Bz along z-axis. The electric field Ey, that is a Hall field, developed along y-axis is directly proportional to Jx as well as Bz. The constant of proportionality, that is a Hall coefficient, has a SI unit of. The Hall coefficient is defined as the ratio of the induced electric field to the product of the current density and applied magnetic field. Its value depends on the type, number and properties of the charge carriers that constitute the current. The Hall voltage Vh equal to Vx into Bz into W Ix Bz by Net. A Hall coefficient Rh equal to Ey by Jx Bz, which comes out to be 1 by Ne. Here N is charge carrier concentration per meter cube, E is charge on the electron coulomb, T is thickness of the metal sample meter, W is width of the metal sample, which is also measured in meter. So ultimately the SI unit of Hall coefficient comes out to be meter cube per coulomb. A vibratory motion is represented by x equal to 2a cos omega t plus a cos omega t plus pi by 2 plus a cos omega t plus pi plus a by 2 cos omega t plus 3 by 2. The resultant amplitude of the motion is amplitudes of individual components a1 equal to 2a, a2 equal to a, a3 equal to a and a4 equal to a by 2. The phase difference between each component is pi by 2. So the resultant amplitude you can see from the graph comes out to be root 5 times a by 2. A force F acting on a body is dependent on its displacement as F proportional to S power minus 1 by 3. Therefore, the power delivered by the force varies with its displacement as force acting on the body F equal to K into S power minus 1 by 3, where K is a proportionality constant. Acceleration of the body A equal to F by M, so it is K by M S power minus 1 by 3. Velocity of the body can be taken from acceleration dV by dt equal to K by M S power minus 1 by 3. Multiply and divide with ds, we obtain VdV equal to K by M S power minus 1 by 3 ds. Now integrating, we get the expression for velocity as V equal to K into S power 1 by 3. So the power delivered P equal to force into velocity, that is Ks power minus 1 by 3 into Ks power plus 1 by 3. Ultimately it comes out to be S power 0. Bamboo strips are hinged to form 3 rhombi as shown. Point A0 is fixed to a rigid support. The lengths of the side of the rhombi are in the ratio 3:2:1. Points A3 is pulled with a velocity V. Let VA1 and VA2 be the speeds with which points A1 and A2 move. Then the ratio VA1 to VA2 is. From the properties of rhombi, A0 A1 is to A1 A2 is to A2 A3 is 3A is to 2A is to A, that comes to be 3 is to 2 is to 1. The hinge A1 will pull the segment A0 A1. The hinge A2 will pull the segment A0 A2, that is equal to A0 A1 plus A1 A2. The hinge A3 will pull the segment A0 A3, that is equal to A0 A1 plus A1 A2 plus A2 A3. Speed of the hinge A3 is given to be V, so the speeds of hinges A1 A2 will be in the ratio of their respective lengths. So VA1 is to VA2 equal to A0 A1 is to A0 A2, which comes out to be 3 is to 3 plus 2, that is 3 is to 5. A particle of mass m is made to move with uniform speed v along the perimeter of a regular hexagon. Magnitude of impulse applied at each corner of the hexagon is. Initial momentum of the particle P initial equal to m into v. Final momentum of the particle P final equal to m into v. Change in momentum of the particle delta P equal to P final minus P initial, which is root of mv whole square plus mv whole square plus 2 times mv into cos 120, because as the particle moves from one side to another side of the hexagon, the change in angle is 120 degrees. So the expression simplifies to mv. Two chambers of different volumes, one containing m1 gram of gas at pressure P1 and other containing m2 gram of same gas at pressure P2, are joined to each other. If the temperature of the gas remains constant, the common pressure reached is. Number of moles of the gas remaining constant, so N1 plus N2 equal to N. So it is P1 V1 by RT plus P2 V2 by RT equal to PV1 by RT plus PV2 by RT, from which we get the expression for P to be P1 V1 plus P2 V2 by V1 plus V2. Applying ideal gas equation, P1 V1 equal to M1 by M RT, from where we get V1 equal to M1 by capital M RT by P1. Similarly, V2 equal to M2 by capital M RT by P2. From which we get the common pressure P equal to P1 V1 plus P2 V2 by V1 plus V2. Substituting the values of V1 V2 in this expression, we get the common pressure as M1 plus M2 of P1 P2 by M1 P2 plus M2 P1. The expression is in terms of mass and pressure. Two liquid drops of equal radii are falling through air with a terminal velocity v. If these two drops collides to form a single drop, its terminal velocity will be. Terminal velocity of the spherical object v equal to 2 by 9 r square g rho naught minus rho m by eta. Here rho naught is density of the object and rho m is the density of the medium. From where we get v is proportional to r square. Radius of each drop is r. Radius of the bigger drop, let us say capital R. Volume of bigger drop should be equal to sum of volumes of the smaller drops. So 4/3 pi r cube equal to 2 times 4/3 pi small r cube, from where we get capital R equal to 2 power 1 by 3 into small r. Terminal velocity of the bigger drop in terms of small v can be taken by taking the ratio v by v equal to r by capital R whole square, from which we have capital V equal to cube root of 4 into small v. An elevator of mass capital M is accelerated upward by applying a force capital F. A mass M is initially situated at a height of 1 meter above the floor of the elevator is falling freely. It will hit the floor of the elevator after a time equal to. Acceleration of the freely falling body is g meter per second square. Acceleration of the elevator A equal to F by M. Acceleration of the body relative to the lift A relative equal to A plus G, that is F by M plus G, that is F plus mg by M. distance traveled by the stone S equal to ut plus half into A relative into t square, that comes out to be 0 plus half into A relative into t square. So from there t equal to root of 2m by f plus mg. The formation of solid argon is due to van der Waals bonding. In this case, the potential energy as a function of interatomic separation can be written as ER equal to minus A r power minus 6 plus B r power minus 12, where A and B are constants. Given that A equal to 8 into 10 power minus 77 joule meter power 6 and B equal to 1.12 into 10 power minus 133 joule meter per 12. The bond length of the solid argon is potential energy of the material ER equal to minus A r power minus 6 plus B r power minus 12. Interatomic attractive forces F equal to minus dE by dr, that is minus d by dr of minus A r power minus 6 plus B r power minus 12, from which we get F equal to 6A r power minus 7 minus 12B r power minus 13. For equilibrium, force is 0, so we get r power 6 equal to 2B by A. Upon substituting the values, we have r power 6 equal to 0.0028 into 10 power minus 54. So r equal to 0.0028 into 10 power minus 54 whole power 1 by 6, which comes out to be 0.375 nanometer. Let A and B be the points respectively above and below the Earth's surface, each at a distance equal to half of the radius of the Earth. If the acceleration due to gravity at these points be GA and GB respectively, then GB is to GA is acceleration due to gravity at a height h, GH equal to G times R by R plus H whole square. Upon substituting the given value, we get GH equal to 4G by 9. Acceleration due to gravity at a depth d, GD equal to G of 1 minus d by R. By putting the values, we get GD equal to G by 2. So GB by GA equal to G by 2 is to 4G by 9, which is 9 is to 8. Let VRMS, VMP and VAVG represent the root mean square, the most probable and average velocities respectively in case of gaseous system in equilibrium at certain temperature. Then VRMS is to V most probable is to V average is. Root mean square velocity of the gas molecule VRMS equal to root of 3RT by M. Most probable velocity of the gas molecule V most probable equal to root of 2RT by M. Average velocity of the gas molecule V average equal to root of 8RT by pi M. Taking the ratio, we get it to be root 3 is to root 2 is to root 8 by pi, which becomes 3 pi is to 2 pi is to 8 after rearrangement. In the arrangement of resistances as shown below, the effective resistance between the points A and B is. See the circuit diagram carefully. Due to the symmetry in the circuit, we can remove the joint at O. After this, we have two balanced Wheatstone's bridges as shown. The circuit can be redrawn as shown in figure. Effective resistance between A and B comes out to be 9 ohm. A block of material of specific gravity 0.4 is held submerged at a depth of 1 meter in a vessel filled with water. The vessel is accelerated upward with an acceleration g by 5. If the block is released at t equal to 0, neglecting viscous effects, it will reach the water surface at t equal to net force acting on the block F net equal to ma. So that is buoyancy force minus gravitational force equal to ma. M dash of g plus a naught minus m of g plus a naught equal to ma. Mass can be written as volume into density. So volume into rho liquid into g plus a naught minus volume rho solid of g plus a naught equal to volume into rho solid into a. from which we get A equal to G plus A naught rho liquid minus rho solid by rho solid. Upon rearranging the terms and substituting the given values, we get A equal to 18. Time taken by the block to travel 1 meter, S equal to ut plus half at square, 1 equal to 0 plus half into 18 into t square. So from which we get t equal to 1 by 3 seconds. The maximum tension in the string of a simple pendulum is 1.2 times the minimum tension. If theta naught is the angular amplitude, then theta naught is equal to maximum tension in the string Tmax equal to mg plus mv square by L. Applying conservation of energy, half mv square equal to mgl of 1 minus cos theta naught, from which v square by L equal to 2g of 1 minus cos theta naught. Tmax is mg plus 2mg of 1 minus cos theta naught, which is mg of 3 minus 2 cos theta naught. Minimum tension in the string T minimum is mg cos theta naught. Given Tmax is 1.2 times T minimum. So by substituting the values, we have theta naught equal to cos inverse of 15 by 16. A plane mirror perpendicular to xy plane makes an angle of 30 degrees with x-axis. An object placed at minus 20, 0 forms an image in the mirror. The point of incidence is 0, 0 and the plane of incidence is xy plane. The coordinates of the image are. See the diagram carefully. From the diagram, we know in the case of a plane mirror, object distance equal to image distance, that is 10. Y coordinate of the image is 20 sin 60, that is 10 root 3. X coordinate of the image is 20 minus 20 cos 60, that is 20 minus 10, that is 10. Both the coordinates are on negative side. So the correct option is minus 10 minus 10 root 3. Magnetic flux through a stationary loop with a resistance R varies during the time interval tau as phi equal to at times tau minus t, where a is a constant. The amount of heat generated in the loop during the time interval tau is. Flux through the stationary loop phi equal to at times tau minus t, that is at tau minus at square. EMF induced in the loop E equal to d phi by dt, that is at minus 2at. Rate of heat generated dH by dt is nothing but E square by R. So it is at minus 2at square by R. So upon integrating, we have h equal to integral dh, integral 0 to tau a tau minus 2at whole square by R dt. Perform the integration and substitute the limits. We have heat generated equal to a square tau cube by 3R. Four functions are given below. Describe the motion of a particle. Y equal to sin omega t minus cos omega t, y equal to sin cube omega t, y equal to 5 cos 3 pi by 4 minus 3 omega t, y equal to 1 plus omega t plus omega square t square. Therefore, simple harmonic motion is represented by y equal to sin omega t minus cos omega t, that is root 2 times 1 by root 2 sin omega t minus 1 by root 2 cos omega t, which simplifies to root 2 times sin of omega t plus 45. So this represents an SHM with an amplitude of root 2 and initial phase 45 degree. Y equal to 5 cos 3 pi by 4 minus 3 omega t, that is 5 cos 3 omega t minus 3 pi by 4. It is an SHM with amplitude 5 and initial phase of minus 3 pi by 4. A magnetic field is established with the help of a pair of north and south poles as shown. A small bar magnet placed freely in the field will undergo pure translational motion, pure rotational motion superimposed on translation motion, oscillatory motion. From the configuration of the magnetic poles, we can see magnetic field created is non-uniform. When a bar magnet is placed in a non-uniform field, it will experience a force as well as torque. So the bar magnet will undergo rotational motion superimposed on translational motion. In a hydrogen atom, the magnetic field at the center of the atom produced by an electron in nth orbit is proportional to magnetic field at the center of the circle B equal to mu naught I by 2r. Current in the circular orbit I equal to E by T, that is E by 2 pi r by V. Radius of the nth orbit r equal to 0.529 n square. Speed of the electron in the nth orbit is 2.2 into 10 power 6 by n. So the magnetic field B equal to mu naught I by 2r, that is mu naught times EV by 2 pi r by 2r. Upon substituting the given values, we get magnetic field is proportional to n power minus 5. A particle of mass m carries a charge plus q. It enters into a region of uniform magnetic field B existing below the line L dash as shown. The time spent by the particle in the magnetic field is. You see the diagrammatic representation properly. The angle covered by the particle inside the field is 2 pi minus 2 theta. That comes out to be pi plus 2 theta. Speed of the charged particle V equal to BQR by m. We can write V equal to R omega. So R omega equal to BQR by m. From there omega equal to BQ by m. Time spent by the particle in the field T equal to angular displacement by angular velocity. So it is pi plus 2 theta by BQ by m, which comes out to be pi plus 2 theta of m by QB. A 2 microfarad capacitor is charged as shown in figure. The change in the stored energy after the switch S is turned into position 2 is. Initial energy stored in 2 microfarad capacitor U initial equal to half CV square, that is V square. Common potential acquired by the system after the switch is thrown to position 2 is Vcom equal to C1V1 plus C2V2 by C1 plus C2. So that comes out to be V by 5. Final energy stored in 2 microfarad capacitor is U2 equal to half into C into Vcom square, that is V square by 25. So the change in stored energy will be U1 minus U2 by U1 into 100, which comes to be 96%. An infinite number of charges equal to 0.2 microcoulomb are arranged in a line at distances 1, 2, 4, 8, so on m from a fixed point. The potential at the fixed point is. Potential due to a point charge V equal to kq by r. Potential due to infinite number of point charges V equal to kq by r1 plus kq by r2, so on. So V equal to kq of 1 by r1 plus 1 by r2, so on. V equal to 9 into 10 power 9 into 0.2 into 10 power minus 6 of 1 by 1 plus 1 by 2 plus 1 by 2 square, so on. Upon simplification, we get the potential to be 3600 volt. A ball of mass m moving with speed u along a direction making an angle theta with the vertical strikes a horizontal steel plate. The collision lasts for a time interval t. If E is the coefficient of restitution between the ball and the plate, the average force exerted by the plate on the ball is. There is no change in momentum along the surface. Mu sin theta equal to mv sin phi, from where we get u sin theta equal to v sin phi. Coefficient of restitution E equal to relative velocity of separation to relative velocity of approach, that is along the normal. So E equal to V cos phi by U cos theta, from where we get V cos phi equal to EU cos theta. Average force exerted by the plate on the ball is delta P by delta T, m of V cos phi minus U cos theta by T, which comes out to be E plus 1 times mu cos theta by T. In YDSC, sources of equal intensities are used. Distance between slits is d and wavelength of light used is lambda. Angular separation of the nearest points on either side of central maximum, where intensities become half of the maximum value, is. Intensity at a point on the screen I equal to I max cos square phi by 2. Here I is I max by 2, so we get phi equal to 90. Relation between path difference and phase difference, delta x equal to 5 by 2 pi into lambda, which gives us the path difference to be lambda by 4. Now path difference delta x equal to d sine theta, that is equal to lambda by 4, which gives us theta equal to lambda by 4d. Since we need to find the angle on either side of central maximum, so it is 2 theta, which comes out to be lambda by 2d. The variation of magnetic field along the axis of a solenoid is graphically represented by magnetic field along the axis of a solenoid B equal to mu naught In by 2 of cos theta 2 minus cos theta 1. If the length of the solenoid is very much greater than its radius, then theta 1 becomes 180 and theta 2 becomes 0. So B equal to mu naught In. So the correct graph is D. A wooden cube is placed on a rough horizontal table. A force is applied to the cube. Gradually, the force is increased. Whether the cube slides before toppling or topples before sliding is independent of the position of point of application of force, the length of the edge of the cube, mass of the cube, coefficient of friction between the cube and the table. Condition for sliding: F is greater than small f times mu mg. Condition for toppling: tau is greater than n times a by 2. That implies tau is greater than mg times a by 2. That is F into h is greater than mg times a by 2, which gives us force to be greater than mga by 2h. The block will slide before toppling if mu mg is less than mga by 2h, that is mu is less than a by 2h. The block will topple before sliding if mu is greater than a by 2h. Whether the cube slides before toppling or topples before sliding thus is independent of mass of the block. The wavelength of sodium line observed in the spectrum of a star is found to be 598 nanometer, whereas that from sodium lamp in the laboratory is found to be 589 nanometer. Therefore, the star is moving with a speed of about wavelength of sodium line in the laboratory lambda equal to 589 nanometer, the actual value. Wavelength of sodium line from the star lambda dash equal to 598 nanometer, the apparent value. As the apparent wavelength is more than the actual wavelength, the star is moving away from the earth. Doppler effect in light: delta lambda by lambda equal to V by C, that gives you V equal to 4.58 into 10 power 6 meter per second. In a series LCR circuit, impedance Z is same at two frequencies F1 and F2. Therefore, the resonant frequency of the circuit is. Impedance of the LCR series circuit is given by Z equal to root of R square plus XL minus XC whole square. Resistance R is independent of frequency. Given ZF1 equal to ZF2, that is XF1 equal to XF2. XL minus XC at F1 equal to XC minus XL at F2. Upon simplifying these values, we get a root of F1 F2 equal to 1 by 2 pi root LC, which is nothing but resonant frequency. Two particles are moving along x and y axis towards the origin with constant speeds u and v respectively. At a time t equal to 0, their respective distances from the origin are x and y. The time instant at which the particles will be closest to each other is. From the diagram, we can see z square equal to x minus ut whole square plus y minus vt whole square. Differentiating with respect to time, 2z dz by dt equal to 2 times x minus ut of minus u plus 2 times y minus vt of minus v. For the distance to be minimum, applying maxima minima condition, we have dz by dt equal to 0. Putting the differentiated value equal to 0, we get t equal to ux plus vy by u square plus v square. A container of volume 0.1 meter cube is filled with nitrogen at a temperature of 47 degrees centigrade and at a gauge pressure of 4.0 into 10 power 5 Pascal. After some time, due to leakage, the gauge pressure drops to 3.0 into 10 power 5 Pascal and the temperature to 27 degrees centigrade. The mass of nitrogen that has leaked out about is absolute pressure equal to gauge pressure plus atmospheric pressure. Applying ideal gas equation PV equal to nRT, we get PV equal to m by m RT. P1 by P2 equal to m1 by m2 T1 by T2 because other factors are constant, from which we get m1 by m2 equal to 75 by 64. Initial mass of the nitrogen gas m1 equal to PVm by RT, which is 0.53 kg. So we get m2 equal to 0.45 kg. Mass of the nitrogen that has leaked out is m1 minus m2, which is 0.53 minus 0.45 equal to 80 gram. 90% of radioactive sample is left over after a time interval t. The percentage of initial sample that will disintegrate in a time interval 2t is percentage radioactive material remaining n by n naught into 100 equal to 1 by 2 whole power t by t into 100, where capital T is a half-life. 90 equal to 1 by 2 whole power t by t into 100, from which we get 0.9 equal to 1 by 2 whole power t by t. Now for the second case, x equal to 1 by 2 whole power 2t by t into 100, that is x equal to 1 by 2 whole power t by t whole square into 100, which gives us the value of x to be 81%. So the percentage radioactive sample that has disintegrated is 100 minus 81, that is 19%. A circuit is arranged as shown. At time t equal to 0, the switch S is placed in position 1. At t equal to 5 seconds, the contact is changed from 1 to 2. The voltage across the capacitor is measured at t equal to 5 seconds and at t equal to 6 seconds. Let these voltages be V1 and V2 respectively. Then V1 and V2 are charge on the capacitor being charged Q equal to Q naught of 1 minus e power minus t by RC. Dividing this equation with capacitance, we get Vc equal to V naught of 1 minus e power minus t by RC. Here R is 20 kilo ohm and C is 100 microfarad, which gives us the potential across capacitor to be 9.18 volt. Voltage across a discharging capacitor R equal to 10 kilo ohms and C equal to 100 microfarad, Vc equal to V naught of e power minus t by RC, which gives us 3.37 volt. There are two thermocouples A and B made up of same pair of metals. In A, each wire is 50 cm long and in B, each wire is 150 cm long. Both the thermocouples are maintained between the same lower temperature θ1 and higher temperature θ2. Each of the two thermocouples is connected to the same microammeter successively. Let E be the thermo EMF and I be the thermoelectric current. Then which of the following statements is true? Both E and I are equal for A and B. Both E and I are greater for B than those of A. E is same for both but I is greater for A. E is same for both but I is greater for B. Resistance of a wire is proportional to its length, so the thermocouple B has more resistance. Thermo EMF of a thermocouple E equal to A theta plus B theta square, where A and B are constants. Theta is the temperature difference, that is theta 2 minus theta 1. Since temperature difference and materials are same for both cases, E is same for both, but I is greater for A as its resistance is less. Two identical particles move at right angles to each other, possessing de Broglie wavelengths lambda 1 and lambda 2. The de Broglie wavelength of each of the particles in their center of mass frame will be. The two particles are identical, so m1 equal to m2 equal to m. De Broglie wavelength of a particle lambda equal to h by mv we have lambda 1 equal to h by mv1 and lambda 2 equal to h by mv2. Since the particles are moving at right angles, velocity of center of mass frame will be v equal to root of v1 by 2 whole square plus v2 by 2 whole square. De Broglie wavelength of the particle in the center of mass frame will be lambda equal to h by mv, that is h by m times root of v1 by 2 whole square plus v2 by 2 whole square. Upon simplification, that comes out to be 2 times lambda 1 lambda 2 by root of lambda 1 square plus lambda 2 square. The stopping potential for a photoelectrons emitted from surface illuminated by light of wavelength 400 nanometer is 500 millivolt. When the incident wavelength is changed to a new value, the stopping potential is found to be 800 millivolt. New wavelength is about. Einstein's photoelectric equation E equal to phi plus EV, that is Hc by lambda equal to phi plus EV. The value of Hc is approximately 1240 electron volt nanometer. So 1240 by 400 equal to phi plus E into 500. 1245 lambda equal to phi plus E into 800. Upon solving these two equations, we get a lambda equal to 365 nanometer. For the logic circuit given below, the output Y for A equal to 0, B equal to 0 and A equal to 1, B equal to 1 are. See the logic circuit carefully. X equal to B bar and Y equal to A bar, since these two are not gates. P equal to X into A, that is B bar A, Z equal to Y into B, that is A bar B. So the final output equal to A bar B plus B bar A. This is an exclusive OR gate. The truth table is given below. So for the given inputs, the outputs are 0 and 0. In a hydrogen-like atom, electron makes transition from an energy level with quantum number n to another with quantum number n minus 1. If n is very much greater than 1, the frequency of radiation emitted is proportional to. Rydberg formula 1 by lambda equal to R of 1 by n initial square minus 1 by n final square into z square for a hydrogen-like atom. Multiplying throughout with the c, speed of light, we get c by lambda equal to Rc times 1 by n initial square minus 1 by n final square into z square. So F equal to Rc times 1 by n minus 1 whole square minus 1 by n square. Upon simplification, we get F is proportional to 1 by n cube. Consider an electron orbiting the nucleus with speed v and in an orbit of radius r. The ratio of magnetic moment to the orbital angular momentum of the electron is independent of magnetic moment of orbiting electron m equal to I into a, that is q by t into pi r square, which gives us half qvr. Angular momentum of the orbiting electron L equal to mvr. Taking the ratio, we get m by L equal to q by 2m. A current I0 enters into a parallel combination of resistors R1 and R2. Current I1 flows through R1 and I2 through R2. The current I0 distributes in such a way that power consumed in R1 and in R2 is the same. Total power consumed in R1 and R2 is minimum. I1 is proportional to R2 and I2 is proportional to R1. The power consumed in each of R1 and R2 is minimum. The two resistors are in parallel. Potential drop is same and I0 equal to I1 plus I2. Since they are parallel, I can write I1 R1 equal to I2 R2, that is I1 R1 equal to I0 minus I1 into R2, from which we get I1 equal to R2 by R1 plus R2 into I0. On similar lines, we get I2 equal to R1 by R1 plus R2 into I0. Weight of a body on the surface of the earth depends on distance of the body from the center of the earth, the latitude of place on the earth surface where the body is placed, the longitude of the place on the earth surface where the body is placed, the angular speed of rotation of the earth about its own axis. Weight of the body W equal to mg. Here m is mass of the object that remains constant, while g is acceleration due to gravity that changes due to different factors. Now variation of g with altitude, that is height, gh equal to g of 1 minus 2h by r. With depth, gd equal to g of 1 minus d by r. With latitude and rotation, g phi equal to g minus r omega square cos square phi, where omega is the angular speed of rotation and phi is the latitude. So A, B, D are correct options. Which of the following are involved in the formation of raindrops in a cloud? Surface tension. This property helps raindrops to attain spherical shape. Temperature. High temperature helps in faster evaporation process and low temperature helps in condensation of the water vapor. Saturation of vapor pressure. This factor decides the rate of evaporation of water from different sources like lakes, rivers and oceans. So the correct options are A, B and D. A cyclic process on PV diagram is as shown below. The same process can be shown on PT and VT diagrams. Choose the correct options from the given graphs. 1 to 2 is isobaric process, pressure is constant. 2 to 3 is isothermal process, temperature is constant. 3 to 4 is isochoric process, volume is constant. 4 to 1 is isothermal process, so temperature is constant again. So A and B are correct options. When a bright light source is placed 30 cm in front of a thin lens, an erect image is formed at 7.5 cm from the lens. A faint inverted image is also formed at 6 cm in front of the lens due to reflection from the front surface of the lens. When the lens is turned around, this weaker inverted image is now formed at 10 cm in front of the lens. Therefore, the lens is diverging biconcave. Applying lens formula 1 by V minus 1 by U equal to 1 by F, we get F equal to minus 10 cm, indicating that it is a diverging lens. Inverted image is formed by concave mirror. The second surface acts as a mirror. Applying mirror formula 1 by V plus 1 by U equal to 1 by F, we get F equal to 5 cm. Radius of curvature of the surface R1 equal to 2 times focal length, that is 10 cm. When the lens is turned around, the second inverted image is formed at 10 cm. So the mirror formula 1 by V plus 1 by U equal to 1 by F, which gives us F equal to 30 by 4 cm. Radius of curvature of the surface R2 equal to 2 times focal length, which comes out to be 15 cm. Now for the refractive index, applying lens maker's formula 1 by F equal to n minus 1 of 1 by R1 minus 1 by R2. By substituting the values with the proper sign convention, we get n equal to 1.6. Applying lens maker's formula when the lens is placed in a liquid, 1 by F liquid equal to n lens by n liquid minus 1 of 1 by R1 minus 1 by R2. So which gives us F liquid equal to 30 cm. Let N1 and N2 moles of two different ideal gases be mixed. If the ratio of specific heats of the two gases are gamma 1 and gamma 2 respectively, then the ratio of specific heats gamma of the mixture is given through the relation. Resultant CV is N1 CV1 plus N2 CV2 by N1 plus N2. That gives us N1 plus N2 of CV equal to N1 CV1 plus N2 CV2. CV can be written as R by gamma minus 1. Ultimately it comes out to be N1 plus N2 by gamma minus 1 equal to N1 by gamma 1 minus 1 plus N2 by gamma 2 minus 1. Resultant Cp equal to N1 Cp1 plus N2 Cp2 by N1 plus N2. Cross multiplying N1 plus N2 of Cp equal to N1 Cp1 plus N2 Cp2. Rearranging the terms, we have N1 plus N2 of gamma by gamma minus 1 equal to N1 of gamma 1 by gamma 1 minus 1 plus N2 of gamma 2 by gamma 2 minus 1. A resistance of 4 ohm is connected across a cell. Then it is replaced by another resistance of 1 ohm. It is found that the power dissipated in resistance in both cases is 16 watt. Then internal resistance of the cell is 2 ohm, EMF of the cell is 12 volt. Maximum power that can be dissipated in the external resistance is 18 watt. Short circuit current from the cell is infinity. Current through the circuit I1 equal to E by R plus R, that is E by 4 plus R. Current through the circuit I2 equal to E by R plus R, that is E by 1 plus R in the second case. Given that power dissipated in both cases is same, power dissipated is I square R. So from there we get internal resistance equal to 2 ohms. Now according to the given condition, E by 4 plus R whole square into 4 equal to 16, from which we have E equal to 12 volt. Maximum power is transferred when internal resistance of the circuit equal to external resistance. So P max equal to E square by 4R square into R, that is 18 watt. Two solid spheres A and B of equal volumes but of different densities dA and dB respectively are connected by a string. They are fully immersed in a fluid of density d fluid. They get arranged in equilibrium state as shown in figure with non-zero tension in this string. The arrangement is possible only if, for equilibrium of the system, 2 times V into d fluid into G equal to V into dA into G plus V into dB into G, that is gravitational force equal to buoyancy force, from which we get 2 times d fluid equal to dA plus dB. Here d represents density. For non-zero tension in the string, V into dF into G should be greater than V into dA into G. That implies dA is less than dF. Similarly, V into dB into G should be greater than V into dF into G. That implies dB is greater than dF. A particle Q moving along positive y-axis. Another particle P is moving in xy plane along a straight line x equal to minus d, where d is greater than 0, with a uniform speed v parallel to that of Q. At a time t equal to 0, particles P and Q happen to be along x-axis, where a third particle R situated at x equal to plus d starts moving opposite to P with a constant acceleration a. At all further instants, the three particles happen to be collinear. Then Q has an initial speed of v by 2, will come to rest after a time interval of v by a, has an acceleration of minus a by 2, will return to its initial position after a time interval of 2v by a. See the diagram carefully at t equal to 0 and at t equal to t. Since the particles are collinear at all times, the slopes are equal. So yq minus yp equal to yr minus yp by xr minus xp of x plus d. That gives yq minus vt equal to minus half at square minus vt by 2d of x plus d. Putting x equal to 0 and differentiating, we have vq minus v equal to minus at minus v by 2d into d, which simplifies to minus at minus v by 2. For initial velocity of q put equal to 0, we have vq equal to v minus v by 2, that is v by 2. Differentiating equation 1 with respect to time, aq minus 0 equal to minus a minus 0 by 2, that is minus a by 2, that is the time differentiation of velocity is acceleration. Put vq equal to 0 in equation 1, we have 0 minus v equal to minus at minus v by 2, which gives us t equal to v by a. Since the acceleration is constant, the particle q will return to its starting point in a time equal to 2t, that is 2 times v by a. A 40 watt 120 volt incandescent bulb has a tungsten filament 0.381 meter long. The diameter of the filament is 33 micrometer. Tungsten has a resistivity 5.51 into 10 power minus 8 ohm meter at room temperature 20 degrees centigrade. Given that the resistivity of the tungsten filament varies as T power 6 by 5, estimate the temperature of the filament when it is operated at its rated voltage. Resistance of the wire at room temperature R1 equal to rho L by A, that is rho L by pi d square by 4, which gives us 24.5 ohm. Resistance of the wire at full power consumption is R2 equal to V square by P, which gives us 360 ohm. Resistivity of the wire at full power consumption rho equal to R2 into A by L, that is R2 into pi d square by 4 by L, which comes out to be 8.08 into 10 power minus 7 ohm meter. Relation between resistivity and temperature is given as rho is proportional to T power 6 by 5. Upon substituting the values here, we get T1 equal to 2746.3 Kelvin. Coming to the next bit, power radiated by the body P equal to sigma AE T power 4, where sigma is Stephen Boltzmann's constant, E is emissivity, A is surface area and T is temperature. Here it can be written as sigma times 2 pi r into L, because the filament is taken to be a cylinder, into E T power 4 minus T naught power 4. T naught is the surrounding temperature. By substituting the values, we get the temperature of the filament to be 2672.3 Kelvin. A parallel plate capacitor with a separation D equal to 1 cm is subjected to a potential difference of 20 kV with air as dielectric. Assume that the air behaves as a dielectric insulator up to a maximum electric field called the dielectric strength of 30 kV per centimeter, after which it breaks down. Now a thin plate of glass, dielectric constant 6.5 and dielectric strength 290 kV per centimeter is inserted. Determine the maximum thickness of the glass plate to avoid breakdown in the capacitor. Capacitance with dielectric C1 equal to K times epsilon naught A by T. Capacitance without dielectric C2 equal to epsilon naught A by D minus T. Potential across the air capacitor V2 equal to C1 by C1 plus C2 into V, which comes out to be K by T times D minus T into T by T plus K into D minus T into V. From there we can write V2 by D minus T, that is equal to KV by T plus K into D minus T. So 30 equal to 20 into 6.5 by T plus 6.5 of 1 minus T, which gives us T equal to 0.394 centimeter. Cauchy's empirical formula for refractive index of a transparent medium is n minus 1 equal to A of 1 plus B by lambda square. Hence obtain the condition for achromatic combination of two lenses made from different glasses. Refractive indices of flint glass and crown glasses are given below. Flint glass 1.644 for 640 nanometer wavelength, 1.664 for 480 nanometer wavelength. Crown glass 1.514 for 640 nanometer wavelength and 1.524 for 480 nanometer wavelength. Dispersive power of flint glass omega 1 equal to mu blue minus mu red by mu blue plus mu red by 2 minus 1. That gives us 2 by 65.4. Similarly, dispersive power of crown glass omega 2 equal to 1 by 51.9. Let us see the condition for achromatism omega 1 by f1 plus omega 2 by f2 equal to 0, from which we have omega 1 by omega 2 equal to minus f1 by f2. So minus f1 by f2 equal to 2 by 65.4 by 1 by 51.9, which gives us f1 equal to minus 1.6 times f2. Effective focal length of the combination 1 by capital F equal to 1 by f1 plus 1 by f2, 1 by 40 equal to 1 by f1 plus 1 by f2, which gives us another relation between f1 and f2. Solving both the equations, we have f2 equal to 15 centimeter, that is for convex lens, and f1 equal to minus 1.6 times f2, that is minus 24 centimeter for concave lens. Given Cauchy's empirical formula for refractive index n minus 1 equal to A times 1 plus B by lambda square. Lens maker's formula 1 by f equal to n minus 1 of 1 by r1 minus 1 by r2. Differentiating this, we get minus 1 by f square df equal to dn times 1 by r1 minus 1 by r2. Divide with the Lensmaker's formula, we get minus df by f equal to dn by n minus 1, which is omega. Effective focal length of the combination 1 by capital F equal to 1 by f1 plus 1 by f2. Differentiating, we have minus 1 by f square df equal to minus 1 by f1 square df1 minus 1 by f2 square df2. Condition for achromatism, df equal to 0, that is minus 1 by f1 square df1 equal to 1 by f2 square df2, which gives us omega 1 by f1 plus omega 2 by f2 equal to 0. Obtain an expression for magnetic moment associated with a solenoid of length L and a number of turns N carrying a current I. The inner and outer radii of the solenoid are R1 and R2. Number of turns per unit length small n equal to capital N by L. Consider the cross-sectional view of the solenoid. Take an elemental radius of R and thickness dr. Number of turns per unit length in this element dn equal to dr by r2 minus r1 into n. Magnetic moment of the elemental solenoid dm equal to I into a into dn, that is dm equal to I into pi r square dr by r2 minus r1 into n, which is after rearranging becomes I pi n by r2 minus r1 into r square dr. So the total moment m equal to integral dm I pi n by r2 minus r1 integral r1 to r2 r square dr. Upon integration, we get the final value as I pi n by 3l r2 minus r1 of r2 cube minus r1 cube. One end of a string is attached to a rigid wall at point O, passes over a smooth pulley and carries a hanger S of mass capital M and its other end. Another object P of mass capital M is suspended from a light ring that can slide without friction along the string as shown in figure. OA is horizontal. Find the additional mass to be attached to the hanger S so as to raise the object P by 10 cm. For equilibrium of the system, 2t cos theta equal to mg, that is 2mg cos theta equal to mg, theta equal to 60 degrees. Tan 60 equal to 20 root 3 by h, from which we get h equal to 20 cm. The block P is to be raised by 10 cm. Now the angle is phi. Tan phi equal to 20 root 3 by 10, that is 2 root 3, which gives cos phi equal to 1 by root 13. For equilibrium of the system, 2t cos phi equal to mg, that is 2 times m plus mg 1 by root 13 equal to mg, which gives us small m equal to root 13 minus 2 by 2 into capital M.